So refer to the first sheet on quadratics. Very quickly we'll go past these problems. I'm hoping you would have attempted the ones that I had asked you to attempt. Let's have these problems solved. Sheet 1. So the first problem is about a quadratic p squared minus 3p plus 2 into x squared minus p squared minus 5p plus 4 into x plus p minus p squared equal to 0. And we want this quadratic to have more than two roots. A quadratic will have more than two roots. That means if it vanishes for more than two values of x, it will vanish for all values of x. That means in order that this quadratic has more than two roots, all its coefficients must be 0. Let me find the value of p for which all the coefficients, coefficient of x squared, coefficient of x and the constant term, all of them become 0. Now this one is simply p minus 1 into p minus 2. This expression is p minus 4 into p minus 1. This expression is p into 1 minus p. Very clearly, p equal to 1 will cause all the three coefficients to become 0. That means if p is 1, then this will be, if p is 1, this expression would be identically equal to 0 and will have infinite number of roots. Yes or no? So p equal to 1 is the required value. Yes or no? Right? Problem 2. There is a quadratic b minus c into x squared plus c minus a into x plus a minus b equal to 0. We want the roots of this quadratic. Now one thing for sure, one of the roots is obtained by inspection. Do you see that? X equal to 1 can be obtained out of inspection. See, for x equal to 1, b minus c plus c minus a plus a minus b, that's clearly 0. Now, if you have one root by inspection, then very clearly the product of the roots, let's say beta is the other root, then the product of the roots would be 1 into beta, right? And that must be a minus b by b minus c, causing the second root beta to be a minus b by b minus c. So the two roots are x equal to 1 and x equal to a minus b by b minus c. Yes. Inspection is observation. I mean, I can see that this is a cyclic set of terms, b minus c, c minus a minus b. They become 0 all by themselves. And if you don't like this inspection business, then you can go elaborate, unnecessarily elaborate, and do the following. Solve the quadratic using the regular means, and you'll again get the same thing. Or you want to factorize this as b minus c into x squared plus c minus b plus b minus a into x plus a minus b equal to 0. If you want to do this, do this. I'm not objecting. See, now you can take c minus b into x along with this, b minus a into x along with this. From these two terms, take a minus b common. From these two terms, take b minus c common and do all that shit. Sorry, but if you want, you can do that. Right? But some things that are readily available by ordinary, mundane, common sense, regular observation, then why go for elaborate means, isn't it? Problem 3. Alpha, beta are the roots of x squared plus px plus q equal to 0. And gamma, delta are the roots of x squared plus px minus r equal to 0. We want to find the value of alpha minus gamma into alpha minus delta. Alpha, beta are the roots of this, gamma, delta are the roots of this, right? We want to find the value of alpha minus gamma into alpha minus delta. Yes or no? Now, if gamma and delta are anyways roots of this, that means this expression must be identically equal to alpha minus gamma into alpha minus delta. Yes or no? Isn't it? Or you could this expression, I mean x minus gamma into x minus delta, this expression could have been written as x minus gamma into x minus delta, and then you can put x equal to alpha here. Yes or no? This expression x squared plus px minus r has roots gamma and delta, so it could be factorized as x minus gamma into x minus delta. X minus gamma into x minus delta. I want the value of alpha minus gamma into alpha minus delta. Is this an equation or an identity? So can you plug in the value of x equal to London? Can you plug in the value of x equal to Patna? So why can't you plug in x equal to alpha on both sides? So put x equal to alpha on both sides because this is an identity. So alpha squared plus p alpha minus r is alpha minus gamma into alpha minus delta. Yes or no? Right? Now, so I just need to simplify this. Realize that alpha is a root of this equation. Alpha is a root of this equation. Therefore, alpha squared plus p alpha plus q must be 0. So I can write alpha squared plus p alpha as minus q. This alpha squared plus p alpha could have been written as minus q. So this becomes minus q minus r. Yes or no? Nahin, confused now? See, this alpha squared plus p alpha I have substituted as minus q. This will become minus q minus r. That's the value of this expression, alpha minus gamma into alpha minus delta. So option C. Fourth, two real numbers alpha and beta are such that alpha plus beta is 3 and mod of alpha minus beta is 4. Mod of alpha minus beta is 4. Then alpha beta are the roots of, we want to find the quadratic whose roots are alpha and beta. Very clearly, the quadratic whose roots are alpha and beta is x squared minus alpha plus beta into x plus alpha beta. So I just need to find the value of alpha beta because alpha plus beta is known, right? Very clearly, alpha beta, 4 times alpha beta is alpha plus beta whole squared minus alpha minus beta whole squared. That's 4 times alpha beta, right? Which means it's 9 minus 16, that is minus 7. Alpha minus beta whole squared, 16. Alpha plus beta, 9 minus, that's minus 7, right? So this alpha beta I can write as minus 7 by 4, right? And this alpha plus beta I can write as 3. So the required equation is x squared minus 3x minus 7 by 4, right? Alpha beta is 7 by 4 equal to 0. Or 4x squared minus 12x minus 7 is 0. Right? A, B, C are integers. A, B, C are integers, that's given in the next problem. And B squared is 4 into AC plus 5D squared. That's given, right? Then the roots of the equation now, what's the discriminant of the quadratic? B squared minus 4AC is the discriminant of this quadratic. But B squared minus 4AC is 20D squared. B squared minus 4AC is 20D squared. Now, in the solution to this, we have minus B plus minus root D by 2A. A and B are rational numbers, are integers, but root D is irrational. Square root of the discriminant, as you can see, is magnitude of D, root 20. But root 20 is irrational. So square root of the discriminant is irrational. Therefore, the roots of this quadratic must be irrational. Right? A, B, C are real numbers. A, B, C are real numbers such that 4A plus 2B plus C is greater than 0 and AB is greater than 0. Then AX squared plus BX plus C equal to 0 has what kind of roots? That's what we need to, whether it has real roots or imaginary roots, exactly one root, none of these. Hey.
So 4A plus 2B plus C is equal to 0 in the question.
Oh, okay. Is equal to 0. Is equal to 0. Right? Now, if I call this expression fx, then what is this? This is f of 2. This is f of 2. Very clearly, f of 2 is 0. That means x equal to 2. Must this vanishes for x equal to 2? Right? That means x equal to 2 is a root of the quadratic. X equal to 2 is a root of the quadratic. Now, A, B, C are real numbers. So, if one root is real, the other root must also be real. So, the quadratic must have both roots real. The quadratic must have both roots real. Yes or no? No observation. This is not observation. See, a quadratic whose coefficients are real numbers will have, if one root is real, the second root will also be real. Because if the second root is complex, then you will have, one real, one complex root. But complex roots always occur in pairs. So you can't have one real root and one complex root. You can't have an odd number of complex roots because they always occur in pairs.
I was understanding why the f of 2 is there. That's what I realized is by observation.
Oh, this one is of course by observation. This is the value of this quadratic at x equal to 2. That means this quadratic vanishes at x equal to 2. X equal to 2 is a real root. If one root is real, the other must also be real, provided the coefficients are all real numbers. Right? Seven. Consider this equation x squared plus 2x minus n is 0, where n is a natural number and n belongs to 5 to 100. Then total number of values of n, so that the given equation has integer roots. We want the given equation to have integer roots. How many values of n belonging to this will cause this equation to have integer roots? That's what we need to figure out. Right? Now, as you can see, this n can be written as x into x plus 2, where x is an integer, n is an integer. We want integer roots of this, right? Such has to be the choice of n from this set, right? N could have been written as x into x plus 2, which is like product of two consecutive integers, where this product should not exceed 5, should not exceed 100, and should be greater than or equal to 5. Right? Because n, that's the, right? So then, the x and x plus 2 combinations can be 1 and 3, for example. Right? These are consecutive. X is 1, x plus 2 would be 3. Then 2 and 4, 3 and 5, 5 and 7, 4 and 6, 5 and 7, 6 and 8, 7 and 9, 8 and 10, 9 and 11, that's all. In this case, 99. After this, if you took x equal to 10, 9 and 12, 9 and 11, sorry. After this, if you took, say for example, x equal to 10, then x plus 2 would be 12. That will exceed 100. Again, 1 into 3 is ruled out because 1 into 3 is not greater than 5. So this is ruled out. So x can have a value 2, x can have a value 3, can have a value 4, can have a value 5, 6, 7, 8, 9. So there are 8 permissible values of x for which n lies in the interval 5 to 100. No, not sure now. Sure now. So 8 values of x. These are the 8 values of x for which this product does not exceed 100 and is greater than or equal to 5. 1 into 3 is 3, but n can't be 3 because n is always greater than or equal to 5, right? And all these other values are acceptable because 9 into 11, 99, which does not exceed 100. After this, if you took x equal to 10, then that will be 10 into 12, which will exceed 100. So n will become greater than 100, which is not the case. So 8 values of x, which will cause 8 integer roots of this, such that n lies in the interval 5 to 100. Clear? K into 6x squared plus 3 plus Rx plus 2x squared minus 1 equal to 0 is one quadratic. The other quadratic is 6k into 2x squared plus 1 plus px plus 4x squared minus 2 equal to 0. And these quadratics are known to have both roots common. That means their coefficients must be proportional, right? Now, let me rewrite this quadratic. It's like 6k plus 2 into x squared plus rx plus 3k minus 1 equal to 0, right? This quadratic, 6k plus 4 or 12k plus 4 into x squared plus px plus 6k minus 2 is 0. Very clearly, this by this you can see is 2. This by this you can see is 2, right? Therefore, p by r must be 2. In order that the quadratics have identical roots, their coefficients must be proportional, and ratio of their coefficients, see, this divided by this 2, this divided by this 2. So p by r must be 2. So p by r must be 2, or 2r minus p must be 0. 2r minus p must be 0. Yes or no? Right now? A, B, P, Q are real, non-zero real numbers. Then the two equations, 2a squared x squared minus 2ab x plus b squared equal to 0 is one quadratic. The other quadratic, p squared x squared plus 2pqx plus q squared equal to 0 is another quadratic. We want to see if they have common roots or not. We want to examine if they have common roots or not. See, look at this quadratic. Discriminant of this is 4a squared b squared minus 8a squared b squared, which is minus 4a squared b squared, which is less than 0. That means its roots are both complex. Its roots are both complex, discriminant less than 0, it has imaginary roots. Yes or no? Let's look at this quadratic. The discriminant of this quadratic is 4p squared q squared minus 4p squared q squared, that's 0. Its roots are real and equal. Real and equal. Very clearly, there cannot be common roots. Very clearly, they cannot be common roots. Isn't it? There's a quadratic fx equal to ax squared plus bx plus c, a not equal to 0, a greater than 0, b less than 0, and c less than 0. Right? We want to figure out which of these would represent the graph. So D is ruled out because a greater than 0, it has to be an upward opening parabola. So we need to choose between a, b and c. Right? Now, f0, value of the function at x equal to 0 is c, which is less than 0. Isn't it? Value of the function at x equal to 0 is c, which is less than 0. Now, look at the three graphs. Only b gives me a negative value at x equal to 0. Isn't it? Only in option B. See, option B is like this. At x equal to 0, it assumes a value c which is negative. This is f0. This is the value of the function at x equal to 0, which is clearly negative. C, which is f0, is negative. So this is the only option in which f0 is negative, right? So this must be the right option. Option B must be the right option. And in this case, check whether B is negative or not. Check whether B is negative or not. In this case, do you realize one root is positive, the other root is negative? So the product of the roots must be negative. That means alpha beta must be less than 0. That means C by A must be less than 0. But A is positive, C is negative, which is true for this, right? So this must be the case. Right? So option B. See now, a quadratic expression will bear the same sign if it never crosses the x-axis. It will either be all positive or all negative if it never pays tribute to the x-axis. See? A quadratic strictly above the x-axis is like this. A quadratic strictly below the x-axis is like this. Yes or no? This is a quadratic strictly above the x-axis. That's the equation graph of a quadratic strictly below the x-axis. Now, in both cases, fx has the same sign. It's all positive here and it's all negative here. In this case, for any given x, fx is less than 0. That means this is a quadratic in which the sign of fx is negative everywhere. This is the case in which this is fx is positive for all x. And what's common between these two graphs? No real roots in both cases, right? So in both cases we have discriminant less than 0, b squared less than 4ac, etc. Right? So option B, right? So the graph of a quadratic will be strictly above the x-axis or strictly below the x-axis if its discriminant is less than 0. In which case, it will either be positive for all real x or it will be negative for all real x, right? Now, y equal to x squared plus kx minus x plus 9. Y equal to x squared plus kx minus x plus 9 is strictly above the x-axis. First of all, coefficient of x square is positive, so it must be a upward opening parabola, isn't it? And strictly above the x-axis means this is upward opening because coefficient of x square is positive. And if it doesn't touch the x-axis anywhere, that means if it doesn't cross the x-axis anywhere and strictly above the x-axis, that means discriminant must be less than 0. Discriminant of this is k minus 1 whole squared minus 36 less than 0. That's a discriminant. That means k minus 1 whole squared less than 36 or mod of k minus 1 less than 6. Right? If I take the square root, it will become mod of k minus, but mod k less than this. That means this will give me k minus 1 less than 6 greater than minus 6 or k greater than minus 5 and less than 7. K greater than minus 5 and less than 7 is what you get out of this. Simple? (13) A, B are real numbers and A not equal to 0. And we have a quadratic y equal to fx equal to ax squared minus bx plus 1 equal to 0 has imaginary roots. This has imaginary roots, that's given in the problem. Then a plus b plus 1. We need to determine the sign of a plus b plus 1. We need to determine the sign of a plus b plus 1 given that this quadratic has imaginary roots and given that a, b are real numbers, right? Now, if it has imaginary roots, that means the graph of this will either be strictly above the x-axis or strictly below the x-axis. That means, be it entirely above the x-axis or be it entirely below the x-axis, it will maintain the same sign. This function will maintain the same sign. Either it will be positive for all real x, it will be negative for all real x. If at a sample point it is found to be positive, then at all points it will be positive. If at a certain sample point by inspection we find it's negative, then this expression will be negative for all real x. Yes or no? Right? Now check that out. What is f0? 1, which is positive. That means at x equal to 0, it's found to be positive. That means for all x it must be positive. Right? That means the graph of this must be like this. No real roots and positive for all real x, because if it's found positive for 1x, it will be positive for all x. So one thing for sure, A is positive in this graph, right? Also, we need to ascertain the sign of A plus B plus 1. Hey, what is A plus B plus 1? F of minus 1, isn't it? See, A plus B plus 1 is f of minus 1. The value of this expression at x equal to minus 1. And even at x equal to minus 1, it's going to be positive. That's f of minus 1. Very clearly it's positive. So a sign of A plus B plus 1 is positive. Yes or no? Are you all okay with this? A and B are given to be non-zero, distinct roots of x squared plus ax plus b equal to 0. We want to find the least value of x squared plus ax plus b. We want to find the least value of this expression. Given that a and b are roots of this. Now if a and b are roots of this, then sum of the roots a plus b must be minus a. Yes or no? That's sum of the roots a plus b minus b by a minus a by 1. And the product of the roots ab must be b. That's the product of the roots. Now b is not 0, that's given. Therefore, this would mean that a must be 1. Now if a is 1, plug in a equal to 1, you get b equal to minus 2. So a is 1 and b is minus 2. Now, the graph of this is an upward opening parabola. See? Because coefficient of x square is positive. And it has real roots. So let me just redraw this. The graph of this quadratic with real roots a and b is like this. Yes or no? A equal to 1, b equal to minus 2. Let me be technically correct, not that it will matter. One root positive, the other root negative. A equal to 1 and b equal to minus 2. These are the roots of this quadratic, right? And it assumes a least value on the central line, on the axis of symmetry. That means at x equal to minus b by 2a, right? At a point x naught, it assumes its least value at x equal to x naught, which is minus b in this case, divided by 2 at x equal to minus b by 2a. That means at x equal to minus half, right? So the least value of this expression would be, put x equal to minus half here. So 1/4 minus half into 1 plus minus 2. That will be the least value of this expression. Isn't it? Whatever this turns out to be. Yes or no? Y equal to minus 2x squared minus 6x plus 9. Right? If I have to draw the graph of this, what kind of a graph will it be? Downward opening parabola. Downward opening parabola, right? Now, the graph of this would be a downward opening parabola because a is negative. Coefficient of x square is negative, right? Therefore, if it's a downward opening parabola, then at x equal to minus b by 2a, it will assume a maximum value. That means at x equal to minus b, that means minus of minus 6 divided by 2a. It will assume at x equal to minus b by 2a, it will assume a maximum value, right? So that makes it 6 by 4. That means at x not equal to 3 by 2, put x equal to 3 by 2, it will assume a maximum value. It will never assume a minimum value, it will assume a maximum value at x equal to minus b by 2a. Minus of minus 6 divided by minus 4 at x equal to 3 by 2. Yes or no? Confusion? Oh, I'm sorry, at x equal to minus 3 by 2. I'm so sorry. At x equal to minus 3 by 2. Right? At x equal to minus 3 by 2, it will assume a maximum value. Clear? And you can plug in x equal to minus 3 by 2, you will get the required maximum value of y. You will get the required maximum value of y. Or if you were a little finicky, you could even do it from first. Even if you were in a junior class and didn't know much about parabolas, etc., you could have just said minus 2x squared minus 6x plus 9. You could have written this as minus 2 into x squared plus 3x plus 9, right? Which could have been written as minus 2 into x plus 3 by 2 whole squared. So 9 by 4 I have added, so plus 9 minus 2 into minus 9 by 4. I subtract. Minus 9 by 4 with a minus 2, I subtract this. Right? So then at x equal to minus 1.5, this will be 0 and this will be the required least value of y. This will be the required least value of y. Right? Is it matching? Plus 9. 2 into 9 by 4. So plus 2 into 9 by 4. 9 by 2. 18 plus 9. 27 by 4. Okay. Right? That will be the required. And that happens at x equal to minus 1.5. X is a real number. We want to find the range of this expression, x squared minus x plus 1 divided by x squared plus x plus 1. Same thing like I told you, express it as a quadratic in x. So you end up getting y, if I cross multiply x squared plus y plus 1 into x plus y minus 1 equal to 0. Right? But x is real. It's a quadratic in x. X is real. Satisfying this condition, so discriminant must be greater than or equal to 0. Discriminant greater than or equal to 0. Right? Or y plus 1 whole squared minus 4 into y minus 1 whole squared must be greater than or equal to 0. Right? Or y plus 1 plus 2 into y minus 1, y plus 1 minus 2 into y minus 1 must be greater than or equal to 0. Right? A squared minus b squared. This gives me 3y minus 1 into minus y minus 1. Right? Minus y plus 3. Minus y plus 3 greater than or equal to 0. This is what I get. See? Or 3y minus 1 into y minus 3 is less than or equal to 0. Multiplying with a minus sign, the direction of the inequality will change. Right? Or y minus 1/3 into y minus 3 less than or equal to 0. And from wavy curve method, like I discussed yesterday, 1/3 3. This expression, just forget the right hand side, this expression will have the following sign pro forma. It will be positive for y greater than 3. It will be negative for y lying between 1/3 and 3. And it will be positive for y less than 1/3. So when will this be negative? This will be negative for y lying between 1/3 to 3. Yes or no? So the range of y belongs to 1/3 to 3. Y belongs to 1/3 to 3. Okay, in this case, they've given k, so k belongs to 1/3 to 3. We want to find the real values of a, for which the quadratic 2x squared minus a cube plus 8a minus 1 into x plus a squared minus 4a equal to 0 has roots of opposite sign. If it has roots of opposite sign, means product of the roots must be less than 0. That means product of the roots, if alpha and beta are the roots of this, then the product of the roots must be less than 0. Product of the roots means a squared minus 4a by 2 must be less than 0. Or this will give me a into a minus 4 less than 0. I need to find the values of a for which this will be less than 0. What would I deploy? Wavy curve method. Nodes are a equal to 0, a equal to 4. The sign of this expression would be this. It will be less than 0 for a belonging to 0 to 4. For a belonging to 0 to 4. This expression will be negative, right? So option B. (18) Alpha, beta are the roots of x squared minus 2p into x minus 4 minus 15 is 0. Alpha, beta are the roots of this quadratic. Then the set of values of p for which one root is less than alpha and the other root is, one root is less than 1, the other root is greater than 2. That means one of the roots alpha has to be less than 1, the other root beta has to be greater than 2. We want to find the conditions for which that will happen, right? Now this quadratic y equal to fx is like x squared minus 2px plus 8p minus 15. That's this quadratic. It's an upward opening parabola. Why? Because coefficient of x square is positive, right? Now the graph of this must be like this, therefore, right? Where alpha and beta are the roots. Alpha must be smaller than 1, so 1 must lie somewhere here. And beta must be larger than 2, so 2 must lie somewhere here. So will it not suffice? The value of the function at x equal to 1 is negative. The value of the function at x equal to 2 must be negative. That means f1 must be less than 0 and f2 must also be less than 0. These are the two conditions that will suffice, right? What is f1? f1 is 1 minus 2p plus 8p minus 15. That's f1. 1 minus 2p plus 8p minus 15. That must be less than 0. Or 6p less than 14 or p less than 7 by 3. That's one condition. And the second condition, f2 less than 0. f2 less than 0 means put x equal to 2 here. So this is f1 less than 0. f2 must also be less than 0, isn't it? This is f2 which must be less than 0. f2 is 4 minus 4p plus 8p minus 15. That must be less than 0, right? So that gives me 4p minus 11 less than 0 or p less than 11 by 4. Now this condition must be true and this must also be true. When can both these conditions be true? If P is less than 7 by 3. P is less than 7 by 3, then it will also be less than 11 by 4. So the required condition is P less than 7 by 3. In order that both these conditions hold good, it would suffice if this alone holds good. This is 2.33. This is 2.75. This is smaller. So if it's P smaller than this, it will obviously be smaller than this. So P less than 7 by 3. Clear? Right? So option A. Sorry, option B. Option B. Minus infinity to 7 by 3. Minus infinity to 7 by 3. Option B. (19) Alpha, beta are the roots of 4x squared minus 16x plus lambda equal to 0, right? Alpha is given to be less than 1, greater than 2. Beta is given to be greater than 2, less than 3. Then we want to find how many integer values of lambda exist. How many integer values of lambda exist such that alpha, one root lies between 1 and 2, the other root beta lies between 2 and 3. Okay. Now, this quadratic y equal to fx, which is 4x squared minus 16x plus lambda. That's a quadratic. What will be the graph of this? Upward opening parabola. Upward opening parabola. Where alpha lies between 1 and 2 and beta lies between 2 and 3. Yes or no? F1 must be positive, F2 must be negative, and F3 must be positive. Right? So F1 less than 0 would mean what? 4 minus 16 plus lambda less than 0. Lambda less than 12, that's 1. F1 greater than 0. I'm so sorry. F1 greater than 0. Greater than 0. Lambda greater than 12. See, F1 is greater than 0. 4 minus 16 plus lambda greater than 0. That will give me lambda greater than 12. Right? That's one condition. Now, F2 must be less than 0. F2 must be less than 0. 16 minus 32 plus lambda must be less than 0. F2 must be less than 0, isn't it? See, 16 minus 32 plus lambda or lambda less than 16. That's condition 2. Right? And F3 greater than 0. F3 means 4 into 9, 36 minus 48 plus lambda greater than 0, or that gives me lambda greater than 12. Right? That's condition 3. So if you combine all three conditions, you get lambda greater than 12 less than 16 is what you get. Now, see, I have not applied one condition, discriminant greater than 0. I have not applied. And I still say whatever I have done is right. I have not applied discriminant greater than 0. The condition for real roots, alpha, beta, obviously if they lie between two real numbers, alpha and beta have to be real. But I have nowhere deployed the fact that alpha, beta are real numbers. That means, no, I have not deployed discriminant greater than 0. Yes, absolutely. Very well said. See, the fact that it's positive somewhere and negative somewhere ensures that there is one root which is real, and if one root is real, the second root must also be real. Therefore, it would have been redundant to apply discriminant greater than 0. It was not required. All these conditions automatically meant that discriminant is greater than 0 because there was an inherent change of sign. Between 1 and 2, if it changed sign, that could have happened only if it crossed the axis. That means presence of one real root guaranteed, and therefore the second root also guaranteed. Right, now, of these values of lambda, I am only seeking integral lambda. Therefore, lambda must belong to 13, 14, 15. These are the three values of lambda that are integral, commensurate with the required conditions. Isn't it? There is a cubic equation x cubed minus px squared plus qx minus r equal to 0 is a cubic equation given to us. Okay. And it has, of the three roots, right, it will have three roots. A cubic will have three roots. Two roots are equal in magnitude but opposite in sign. Right. That means one root is alpha, the other one is minus alpha, and the third root is beta. These are the three roots. Right. These are the three roots. Now what about the sum of the roots? Alpha plus minus alpha plus beta. That's sum of the roots. That must be minus of minus p by 1. That means it must be p, sum of the roots of this cubic. Right? So beta must therefore be p. Beta therefore must be p. Hey, but beta equal to p. P therefore is a root of this. One root is beta, which turns out to be p. P therefore is a root of this cubic. P must satisfy this cubic. That means you can put x equal to p. Beta is a root, but beta turns out to be p. So p must satisfy this equation, yes or no? That means put x equal to p. So you get p cubed minus p cubed plus qp minus r equal to 0. Plugging in x equal to p in this. That's one of the roots. Right? So that gives me qp minus r equal to 0 as the required condition. Qp minus r equal to 0 as the required condition. So option C. Yes or no? (21) Alpha, beta and gamma are the roots of x cube minus x minus 1 equal to 0. Are the roots of this. We want to find 1 plus alpha by 1 minus alpha plus 1 plus beta by 1 minus beta and 1 plus gamma by 1 minus gamma. We want to find the value of this. Right? This is what we want to find. Now if I can create an equation with roots 1 plus alpha by 1 minus alpha, 1 plus beta by 1 minus beta and 1 plus gamma by 1 minus gamma. If I can create an equation with these as the roots, then the sum of the roots of that equation would be this. Yes or no? So let me create an equation whose roots are 1 plus alpha by 1 minus alpha, 1 plus beta by 1 minus beta and 1 plus gamma by 1 minus gamma. Alpha, beta, gamma are the roots of this. Let me create a transformation. Y, let me move from x to y. Y equal to 1 plus x by 1 minus x. So when x is alpha, y would be 1 plus alpha by 1 minus alpha. When x is beta, y would be 1 plus beta by 1 minus beta. When x is gamma, y would be 1 plus gamma by 1 minus gamma. Yes or no? So let me create a cubic in y whose roots are these. Right? So when I go from the x domain to the y domain, this is the transformation. It will give me a cubic in y whose roots would be these, because when x's are these, then y's would be these, because from x to y this is the transformation, right? So this is like saying x into 1 plus y is y minus 1, right? X therefore is y minus 1 by 1 plus y. Let me plug in x equal to y minus 1 by 1 plus y. Then the roots of this would be the different values of y. obtained for x equal to alpha, x equal to beta, and x equal to gamma, right? So then this would be x cubed, which is y minus 1 by y plus 1 whole cubed, minus y minus 1 by y plus 1 minus y minus 1 by y plus 1 equal to 0. What will be the roots of this? So if I multiply by y plus 1 whole cubed, this will become y minus 1 whole cubed plus y minus 1 into y plus 1 whole square minus minus 1, sorry, this is minus 1, minus y minus 1 whole cubed is 0. Y plus 1 whole cubed is 0. Yes or no? Yes or no? And when you solve for y from this equation, the roots would be y equal to y1 would be this root, y equal to y2 would be this root, y equal to y3 would be this root. The roots of this would be y1, y2, y3. Now if you collect terms, you'll get like something into y cubed, right, plus something into y squared plus something into y plus something equal to 0. When you simplify this, and this will have roots like y1, y2, y3, and the sum of the roots y1 plus y2 plus y3 will turn out to be minus b by a. So just simplify this, write it in this form, and the required sum of the roots y1 plus y2 plus y3 would be minus b by a. Yes or no? Alpha, beta, gamma are the roots of x minus a into x minus b into x minus c equal to d, where d is not given, is not 0, right? We need to figure out the roots of x minus alpha into x minus beta into x minus gamma plus d equal to 0. We need to figure out the roots of this. Now, that means this equation is satisfied for x equal to alpha, x equal to beta, x equal to gamma. That means x minus a into x minus b into x minus c minus d. This will become 0. This minus d will become 0 for x equal to alpha, x equal to beta, x equal to gamma. That means if you factorize this expression, then x minus alpha must be a factor of this, x minus beta must be a factor of this, x minus gamma must be a factor of this. That means this expression can be factorized as, because alpha is a root, x minus alpha will be a factor. Because x equal to beta is a root of this, will cause this to vanish. That means x minus beta must be a factor. Similarly, x minus gamma must be a factor of this. Yes or no? Do you all understand this? Which means x minus a into x minus b into x minus c is actually x minus alpha into x minus beta into x minus gamma plus d, and this is an identity. Transposing d on this side. Hey, this expression is identical to this expression, right? Very clearly, x minus a is a factor of this expression, so a must be a root of this, b must be a root of this, c must be a root of this, isn't it? This expression will become 0 at x equal to a, at x equal to b, at x equal to c. So what are the roots of this? A, b and c will be the roots of this. A, b and c will be the roots of this. Do you all understand this? Right? So option B. We have a quadratic of this form, mod x squared plus mod x minus 6 equal to 0. Let's solve this quadratic. Now x would either be positive or x would be negative, right? Now if x is positive, then mod x will be equal to minus x, yes or no? Will be equal to x. If x is positive, mod x will be equal to x. So let me find the solution for x greater than 0 first. So mod x equal to x means x squared plus x minus 6 is 0. Or x plus 3 into x minus 2 is 0. This will give me x equal to 2 comma minus 3. But x is greater than 0 for this condition. So minus 3 is ruled out. So this is like x equal to 2, one root. Not x equal to minus 3, because this expression was on the premise that x is greater than 0. So you would rule out x equal to minus 3. X equal to 2 must be therefore a root of this. That's one case, right? So x equal to 2. Now for x less than 0, mod x will be minus x. So replace this mod x by minus x. So then that's second case, x less than 0. Replacing mod x by minus x, so x squared minus x minus 6 is 0. Yes or no? So x minus 3 into x plus 2 is 0. Right? So this gives me x equal to 3 comma minus 2. Hey, but x is less than 0 here. So you would rule out x equal to 3 is ruled out. X equal to 3 is ruled out. Therefore, the required solution to this must be x equal to minus 2. Therefore, what are the two roots of this equation? X equal to plus 2 and x equal to minus 2. Sum of the roots therefore is 0. Right? And then you can verify either sum of the roots is 0, product of the roots is minus 4. 4 roots? No, there are only 2 roots. There are only 2 roots. So D is true, B is true, A is true. Right? 24. Alpha, beta are the roots of ax squared plus bx plus c equal to 0. Alpha plus h and beta plus h are the roots of px squared plus qx plus r equal to 0. Right? That means the difference of the roots here must be the same as the difference of the roots here. Yes or no? The two equations have different roots, but the difference of the roots of this equation is the same as difference of the roots of that equation, right? That means, now what's the difference of the roots here? Alpha minus beta whole squared. That's alpha plus beta whole squared minus 4 alpha beta. Yes or no? Alpha plus beta whole squared means b squared by a squared minus 4 into c by a. So that makes it b squared minus 4ac by a squared. That's the difference in the roots here. Similarly, the difference in the roots there, that means alpha plus h minus beta plus h whole squared. Exactly the same way, instead of b you have q here minus 4pr divided by p squared. Yes or no? Instead of a you have p, instead of b you have q, instead of c you have r. So wherever a and c appear, you replace that by p and r. Wherever b appears, you replace that by q. You get the difference of the square of the difference of the roots? No? And the two must be equal, so b squared minus 4ac must be q squared minus 4pr by p squared. That's one condition. Square of the difference of the roots equal. Clear? Also, the roots of this, sum of the roots, alpha plus h plus beta plus h, is the sum of the roots of this quadratic. That must be equal to minus q by p. Yes or no? Sum of the roots minus q by p, alpha plus h plus beta plus, but alpha plus beta is minus b by a, because alpha beta are the roots of this. So minus b by a plus 2h is minus q by p. That gives me the value of h as half of b by a minus q by p. b by a minus q by p gives me the value of h. A and b are given to be non-zero real numbers, and alpha beta are the roots of x squared plus ax plus b equal to 0. Alpha beta are the roots of x squared plus ax plus b is 0. Number A, we want to find a quadratic whose roots are alpha squared and beta squared. So that, what would that quadratic be? X squared minus alpha squared plus beta squared into x plus alpha squared beta squared equal to 0 would be that quadratic. So very clearly alpha plus beta, as you can see, is minus a for this quadratic, and alpha beta is b, right? So alpha square plus beta square you can find using alpha plus beta whole square minus 2 alpha beta, and alpha squared beta squared, the product of the roots, is alpha beta whole squared. So both alpha squared plus beta squared and alpha beta whole squared you can find and plug into this to get the quadratic whose roots are alpha squared and beta squared, right? Have you checked option A, right? Or okay, you need to check, huh? Option A not correct, but need to check that again. Okay, now option B, quadratic whose roots are reciprocal of the roots of this quadratic, what would you do? Replace x by 1 by x. So if you replace x by 1 by x, so 1 by x squared plus a by x plus b equal to 0, or bx squared plus a plus 1 ax plus 1 is 0, is the quadratic whose roots are reciprocal of the roots of the mother quadratic when you replace x by 1 by x, like I discussed in the last class. Option C, quadratic whose roots are alpha by beta and beta by alpha. Again you can find this sum. This sum is alpha squared plus beta squared by alpha beta, which is like alpha plus beta whole squared minus 2 alpha beta by alpha beta. Alpha plus beta is known, alpha beta is known, you can plug in from there. So you know this value, the sum of the roots of this, alpha by beta and beta by alpha, and the product of the roots is very clearly equal to 1. Therefore the required quadratic would be x squared minus x into alpha by beta plus beta by alpha plus 1 equal to 0 would be the required quadratic, where alpha by beta plus beta by alpha can be obtained from this condition. You need to check that also. Okay, I'll skip this. Okay. Quadratic whose roots are alpha minus 1, beta minus 1. What is it that you would do? Right, put y equal to x minus 1 in this. Then when x is alpha, y would be alpha minus 1. When x is beta, y would be beta minus 1. So put x equal to y plus 1. This will make it x equal to y plus 1, where y will have values like alpha minus 1 and beta minus 1 if x has values like alpha and beta. Right, so in this equation, x square, which is y plus 1 whole square, plus a into y plus 1 plus b equal to 0. Right? It's a quadratic whose roots will be alpha minus 1 and beta minus 1 would be the y's. For x equal to alpha, y would be alpha minus 1. For x equal to beta, y would be beta minus 1. So the roots of this quadratic would be alpha minus 1 comma beta minus 1, right? And which you can of course now simplify. Y square plus y into a plus 2 plus a plus b plus 1 equal to 0. And now instead of y, if you had x, it doesn't matter, you will get the same roots, right? Instead of y, if you plug in some x or y or some t, you will have the same roots. So yes, this option is also correct. This option is, option D, as you can see, is correct. See? Isn't it? 26. The graph of a quadratic y equal to ax squared plus bx plus c is given as something like this, right? For sure, two distinct real roots. So discriminant must be greater than 0. B squared minus 4ac must be greater than 0. That makes option A correct. A is correct, right? Okay. It's a downward opening parabola, so A must be less than 0, right? A less than 0, therefore C is not right. C is not right, right? Now, this is x equal to 0, this is f0. But f0 is C. F0 is C, is less than 0, as you can see. So C is clearly less than 0. C is less than 0. C less than 0 means option D is right. Right? Now alpha beta are both negative. Therefore the sum of the roots minus B by A must be negative, because both roots are negative. That means B by A must be positive. But A is negative, so B must also be negative. B must also be negative. Therefore that makes option B correct also. Option B correct. So A, B, D are correct options. A, B, D are correct options here. Yes or no? (27) In 27, for which of the following is the product ABC negative? That's required. For which of the following is the product ABC negative? Given a quadratic y equal to fx equal to ax squared plus bx plus c. Y equal to fx equal to ax squared plus bx plus c. Now the first case of the graph is given as follows. This is the case. Now in this case, do you realize A is less than 0 because downward opening parabola? Yes or no? This is F0, which is C, is less than 0. C is less than 0. Sum of the roots is negative because both roots are negative. Minus B by A less than 0. So similarly, B by A greater than 0. A is negative, so B must also be negative. So in this case, ABC is negative. In this case, ABC is negative. That's this case. So option A is right. Option B. A is less than 0. A is less than 0, isn't it? This is F0, value of the function at x equal to 0. F0, which is C. C is very clearly greater than 0. Right? Now, what about sum of the roots? What about sum of the roots? This is alpha, this is beta. This is alpha, this is beta. Right? What is sum of the roots? In this case, beta seems like numerically bigger than alpha. If beta is numerically bigger than alpha, then the sum of the roots will be positive. One negative root, one positive root. Very clearly, beta is numerically bigger than alpha. As you can see, this length is more than this length. So beta is numerically bigger than alpha. So sum of the roots must be positive. That means minus B by A must be positive. B by A therefore must be negative. A is negative, so B must be positive. B must be positive. So and then 2 positive, 1 negative. Product of ABC is negative here. Yes or no? Confusion? You agree with this? So this is right. Let me look at option C. So A is right, B is right. C. A is positive. Why? Because it's an upward opening parabola. This is F0, value of the function at x equal to 0, which is C. Positive. C positive. Now, the central line, as you can see from the diagram, is here. This is x equal to minus B by 2A. And it's positive. So, minus B by 2A is positive. So B by A must be negative. B by A must be negative. A is positive. Therefore, A is positive. So B must be negative. A is positive. So B must be negative. So product of ABC is negative here. Negative here. So this is also correct. ABC is negative here. This is A less than 0. Why? Downward opening parabola. This is f0, value of the function at x equal to 0. C is negative here, right? This is the line of symmetry, x equal to minus b by 2a, and minus b by 2a is negative here. So b by a must be positive. If b by a is positive, a negative, so b must also be negative. B must also be negative. So product of ABC, negative. Again the product of ABC, negative. Clear? (28) the roots of a quadratic x1 x2 y equal to fx equal to ax squared plus bx plus c. This is a quadratic. Very clearly a is less than 0. So option A is right. Right? Real roots, discriminant is greater than 0. Real and distinct roots. B squared minus 4ac greater than 0. So B is not right. C greater than 0. The value of the function at x equal to 0, this is f0. f0 which is c. Very clearly C is less than 0. C is less than 0, which makes option C incorrect. Which makes option C incorrect. A and B are of opposite signs. Now, what about sum of the roots? Minus b by a, positive. That means, yeah, b and a must be less than 0. A is negative, so B must be positive. So B is positive. So A and B are indeed of opposite signs. So option D is also correct. Option D is also correct. (29) 1. Hey, by the way, if there is a quadratic ax squared plus bx plus c, you know, if alpha beta are the roots of this quadratic could have been written as a into x minus alpha into x minus beta. Yes or no? Right? Now, if alpha is equal to beta, then this would be a into x minus alpha whole squared, and it becomes a perfect square. It becomes a perfect square, yes or no? Which means a quadratic expression will be a perfect square if it has equal roots. Equal roots means discriminant equal to 0. Yes or no? So a quadratic expression will be a perfect square if its discriminant is equal to 0. Do you see that? This is an identity, and if you put alpha equal to beta, you get this to be a perfect square. That means if alpha is beta, discriminant is 0. So any quadratic expression will be a perfect square if its discriminant is equal to 0. Yes or no? So now the next problem is based on this. 29 part 1. X squared plus 2 into a plus b plus c into x plus 3 into ab plus bc plus ca. A, B, C are real numbers. We want to find the condition so that this expression is a perfect square. When would this expression be a perfect square? If its discriminant is equal to 0. What's the discriminant of this? The discriminant of this is 4 into a plus b plus c whole squared minus 12 into ab plus bc plus ca. This must be 0, right? Or a plus b plus c whole square minus 3 into ab plus bc plus ca is 0, right? This is a square plus b square plus c squared plus twice ab plus bc plus ca. So this expression then becomes a square plus b squared plus c squared minus ab minus bc minus ca is 0. Yes or no? Now this expression could have been written as half of, this is a standard thing to do, a minus b whole square plus b minus c whole square plus c minus a whole square. That's this expression. This is 0. Now this is a and b, a, b, c are real numbers. So a minus b, b minus c, c minus a will also be real numbers. So this is square of a real number which can never be negative. This is also square of a real number which can never be negative. This is also square of a real number which can never be negative. Sum of three non-negative numbers is 0 when each is 0. If you have three non-negative numbers and they add up to 0, then each must be 0. Then each must be 0. This would mean a equal to b equal to c. This is 0, this is 0 and this is 0. But if a, b, c are not all real, then we cannot say a equal to b equal to c. Because square of a complex number can be negative. I square, for example, is negative, isn't it? Square of a complex number can be negative, but square of a real number can never be negative, right? Part 2. It's given that x minus alpha is a factor common to a1x squared plus b1x plus c equal and a2x squared plus b2x plus c. We want to show alpha is x minus alpha is common. When you factorize this, x minus alpha will turn out to be a factor. When you factorize this, x minus alpha will also be a common, will be also a factor. Given this, we want to show that alpha into a1 minus a2 must be equal to b2 minus b1. That's what we want to show, right? Now if alpha, x minus alpha is a factor of this, that means this will become 0 at x equal to alpha, right? That means a1 alpha squared plus b1 alpha plus c must be 0. Again, if x minus alpha is a factor of this, this will become 0 at x equal to alpha, right? That means a2 alpha squared plus b2 alpha plus c must be 0. Yes or no? Now, let me divide by alpha. So I get a1 alpha plus b1 plus c by alpha equal to 0 when I divide this by alpha. Yes or no? When I divide this by alpha, then I get a2 alpha plus b2 plus c by alpha is 0. I need to eliminate c. Realize that's why I did this. Then I subtract. When I subtract, then I get a1 minus a2 into alpha plus b1 minus b2 equal to 0, which actually is this condition. This is elimination only. Yeah. You can do that. Of course you can do that. No doubt about it. You can do that. Find all integer values of a for which the quadratic x squared minus x into a plus 10 plus 10a plus 1 equal to 0 has integer roots. We want to find integer values of a for which this will vanish for integer values of x. Now, I did a similar thing in the last class, bless you. This x square minus x into sum of the roots plus 10a product of the roots. So that means the first three terms can be factorized as x minus a into x minus 10. That equal to minus 1. A is an integer, x is an integer. And product of the, therefore x minus a must be an integer. And x minus 10 must also be an integer. Product of two integers minus 1. One must be plus 1, the other one must be minus 1. So two possibilities, x minus a equal to plus 1, x minus 10 equal to minus 1. That's one possibility. This will give me x equal to 9. This will give me x equal to 9. Put x equal to 9. A therefore will be 8. That's one value of a. Right? The other possibility, x minus a equal to minus 1 and x minus 10 equal to plus 1. This gives me x equal to 11. Now if you plug in x equal to 11, you get a equal to 12. So a equal to 8 and 12. A equal to 8 and 12 will give you integer roots x. I discussed a similar problem yesterday in the class, right? Px is a quadratic, Px which is ax squared plus bx plus c, and Qx is another quadratic which is minus ax squared plus dx plus c, right? Now the statement made here is Px into Qx equal to 0 has 4 complex roots. Now the roots of Px into Qx is 0. See, Px is like ax squared plus bx plus c. Qx is like minus ax squared plus dx plus c. This equal to 0 is about this producing 2 roots, Px equal to 0 producing 2 roots, and Qx equal to 0 producing 2 roots. Yes or no? This into this equal to 0 has 2 roots out of Px being 0 and 2 roots out of Qx being 0. Now, if it has all 4 complex roots, that means the 2 roots of this must be complex and the 2 roots of this must be complex. Only then it will have 4 complex roots. Now, the 2 roots of this will be complex if b squared minus 4ac is less than 0. That's when the 2 roots of this will be complex. The 2 roots of this will be complex if d squared plus 4ac is less than 0. That means this must be true and this must be true. Yes or no? Isn't it? Yes. You have a question?
No, sir, it's okay.
No, ask. Please ask.
Sir, I was saying that then we finally get that b squared plus d squared.
Yeah, absolutely. So if I add these two conditions, we get like a b squared plus d squared less than 0. B and d are real numbers. So b squared is non-negative, d squared is non-negative. Sum of two non-negative numbers cannot be negative. So this leads to an impossible situation, right? Therefore, the original assumption that this has complex roots and this has complex roots must be incorrect. So it cannot have all 4 roots complex. At least one of the 2 equations, Px equal to 0 or Qx equal to 0, must have real roots. Isn't it? (32) If A is to B is to C, A, B and C are all real numbers, and the equations ax squared plus bx plus c equal to 0 and x squared plus 2x plus 9 equal to 0 have a common root. They have a common root. Then we want to find the ratio A is to B is to C. Now, what's the discriminant of this? Negative. That means the 2 roots of this must be complex. The 2 roots of this must be of the form alpha plus I beta and alpha minus I beta must be the roots. Now let's say this is the common root. Suppose this equation has a root alpha plus I beta. Hey, but if one root is alpha plus I beta, then the other root must be alpha minus I beta. Therefore, both these equations have both roots common. If one root is common, then both must be common. That's a necessity. And if these 2 equations have both roots common, their coefficients must be proportional. That means A is to B is to C must be 1 is to 2 is to 9. A is to B is to C must be 1 is to 2 is to 9. These equations, ax squared plus bx plus c equal to 0 and x cubed plus 3x squared plus 3x plus 2 equal to 0 have two common roots. We want to be a, b, c are real numbers. We want to find a is to b is to c. Okay. Now, this I can write as x plus 1 whole cube plus 1 equal to 0. Yes or no? I can write this as x plus 1 whole cube plus 1 equal to 0. Isn't it? A cube plus 1 cube plus 3a squared b plus 3ab squared plus, right? No? Then a cube plus b cube, I could further factorize this as a plus b, x plus 1 into a squared minus ab plus b squared, right? Yes or no? This could further be written as x plus 2 into x squared plus x plus 1 equal to 0. Now, the two roots of this must be common with the two roots of this quadratic. Isn't it? That's the only possibility. It can't have one root common with this and one root x equal to minus 2. Because see, the root of this are complex. So if it has to have at least one root common with this, and if it has one root common with this, the second root must also be common. Why? Because the discriminant of this, as seen from the previous problem also, discriminant of this 1 minus 4ac is negative. So it has both roots complex. So if this equation has one root common with this, it will have both roots common with this. That means ax squared plus bx plus c equal to 0 will have both roots common with x squared plus x plus 1 equal to 0, and therefore the coefficients must be proportional. So a is to b is to c must be 1 is to 1 is to 1. Yes or no? Right? Now I'll come to 34 later. This is more of coordinate geometry, but I'll come to that later. Of this quadratic. Yeah. Yes, it has. You will understand when I do n roots of unity in complex numbers. You will understand that this is only a special case of that. Actually, the roots of this are omega and omega squared. Those are cube roots of unity. Those are cube roots of unity. That's why we'll learn more about that when we come to n roots of unity. Yes, indeed, the two roots of this are x equal to omega squared. They are indeed squares of each other. C less than 0 and ax squared plus bx plus c equal to 0 does not have real roots. That's given. This does not have real roots. A, B, C are real numbers. Then we need to find the sign. SGN means sign, positive, negative, sign of A minus B plus C. We want to find the sign of 9A plus 3B plus C. Given that C is less than 0. And this has no real roots. This is a quadratic y equal to fx, which is like a ax squared plus bx plus c. If it has no real roots, that means it must be either positive for all real x or it is Negative for all real x? A quadratic expression with real coefficients having no real roots means it's either going to be positive for all real x or it's going to be negative for all real x. Now, notice that f0 is c, which is given to be less than 0. That means at x equal to 0, it's negative. That means for all x, it will be negative. Fx must be negative for all x, yes or no? So, if f0 is negative, then fx must be negative. Therefore, what is this? This is f of minus 1. Therefore, f of minus 1, which is a minus b plus c, must be negative. What is this? This is f of 3, isn't it? This is f of 3. F of 3, 9a plus 3b plus c. F of 3 must also be negative. So this is negative, this is negative. Right? Pi to power x is minus 2x squared plus 6x minus 9. We want to find all real solutions to this equation. Now, look at this. Y equal to minus 2x squared plus 6x minus 9. If you draw the graph of this, a is negative, so it's going to be a downward opening parabola. It's going to be a downward opening parabola, yes or no? Right? What's the discriminant of this? 36 minus 72, which is less than 0. Downward opening parabola with no real roots. That means the graph of this must be entirely below the x-axis. No real roots. Downward opening. That means for any given x, this expression y must be negative. That means the right hand side is negative for all real x. Right hand side is negative for all real x. Yes or no? No? I'll explain again. And the left hand side, pi power x is always positive. No matter what x is, pi power x is always positive. So left hand side is positive for all real x. And right hand side is negative for all real x. Therefore, the two can never be equal, so it will not have any real solutions. It will not have any real solutions. Yes or no? Right? (39) Cos square pi by 8 is a root of x squared plus bx plus c equal to 0, where b and c are rational numbers. Q is rational numbers. B and c are rational numbers, and cos square pi by 8 is a root of this. That means the coefficients are all rational numbers. So one root is cos square pi by 8, which is like half of 1 plus cos pi by 4, which is like half of 1 plus 1 by root 2. So if coefficients are rational numbers, then irrational root, this is irrational root. Irrational roots also occur in pairs. Did I tell you this? Right? That means if one root is alpha given as this, the other root would be the conjugate of this, which is half of 1 minus 1 by root 2. Yes or no? Therefore, the sum of the roots alpha plus beta is minus b, and that must be equal to 1. Sum of the roots 1, right? Therefore, b must be minus 1. The product of the roots is c, and if you take the product here, that's 1/4 into 1 minus half. 1/4 into 1 minus half, that makes it 1 by 8. So c is 1 by 8, b is minus 1.